Okay, hello, welcome back everybody. In this video, I want to show how to use Sage Math to diagonalize a matrix, actually orthogonally diagonalize the matrix. So here's a question from Anton. It says, find a matrix P that orthogonalizes a given matrix A. Here are the various possibilities for A. I'm going to do number 11 here. Switch over to Sage Math. All right, so we enter our matrix A, and here's how to do it. It's a 3x3 matrix with entries in the rational numbers. That's what the QQ stands for. And then you just enter the rows of A successfully. Okay, oops, and then turn on the typeset mode. This works in Safari, doesn't work in Firefox, but oh well. And then we ask for A.eigenmatrix right. And what that gives is a list of two 3x3 matrices. This first matrix here consists of the eigenvalues listed along the diagonal. So the eigenvalues of this matrix A turn out to be 0, 3, and 3. So this first matrix is always going to be a diagonal matrix, provided the matrix A can be diagonalized. And then the second matrix here is this matrix that I've been calling P, which is the matrix whose columns are the eigenvectors corresponding to the associated eigenvalue. So for example, the vector 1, 1, 1, this first column, has an eigenvalue of 0. The vector 1, 0, minus 1 has an eigenvalue of 3. Again, what does that mean? That means when you take this matrix A, multiply by 1, 0, negative 1, that column vector, you'll get 3 times 1, 0, negative 1. All right. So then in chapter 5, if all we wanted to do is diagonalize the matrix, we'd be done. These matrices here basically give us the answer. We can collect them into individual matrices by this notation here, D comma P, set it equal to the output on the previous line. What that does is it sets D to the first matrix and P to the second matrix. So here I just ask for P and here D, so you can see what that does. And then recall that diagonalization involves finding these matrices P and D such that P times D times P inverse is back to your original matrix. So this gives a way to factor our original matrix A here as a product of some invertible matrix P, some diagonal matrix D, and some P inverse. Now, what's new in chapter 7 and what we can do for symmetric matrices is we can orthogonally diagonalize. We can insist that the P is an orthogonal matrix. In other words, its columns and rows form an orthonormal basis. And the P that we found so far, unfortunately, is not orthogonal, because when we take P transpose times P, that's what this line does, we do not get the identity matrix back. So we have to fix P so that its columns form an orthonormal basis. And the way to do that is use the Gram-Schmidt process. Now, Sage does have a built-in Gram-Schmidt process. It applies that to, if you give it a matrix, it applies this built-in Gram-Schmidt process to the rows of A, not the columns, rows of the matrix, not the columns of the matrix. And we're kind of interested more in the columns, but that's easy to fix. We just take the matrix and transpose it. So this matrix P, where is it up here? This consists of the eigenvectors. And what's wrong with it? So, well, I mean, what we want is we want eigenvectors that are orthonormal to each other or form an orthonormal basis. Okay, so we then just take the transpose And that's only to just apply the Gram-Schmidt to the rows. And so when I apply this built-in Gram-Schmidt process, it spits out two matrices. We're really interested in the first matrix here. That's the matrix whose now its rows are orthogonal, not orthonormal, but orthogonal. So if you take the dot product of the first and the second row, you get 1 times 1 plus 0 plus -1, which adds to, okay, 1 plus 0 minus 1 is 0. And so we see that the first two rows are orthogonal. Now the norm of the first row is the square root of 1 squared plus 1 squared plus 1 squared, which is 3. So the norm is not 1. It's not a unit vector. So this process of this built-in Gram-Schmidt process does not normalize the vectors to become unit vectors, but instead just does the step of making sure you get an orthogonal basis. Fortunately, it's pretty easy to fix or change these rows into unit vectors. Okay, so let's just capture this first matrix here. That's what we want. So the command for that is just bracket 0. This is hopefully familiar from Python. The numbering starts at 0. And so 0 refers to this first matrix. The 1 index refers to the second matrix in a list of whatever. Okay, so then we're going to take this matrix here. That's what q.Gram-Schmidt bracket and then another bracket 0. And then I want to convert the rows back into columns. So that's why I took the transpose. Okay, so I've got this matrix R, and maybe I should just show you what R looks like. So R is just this matrix here, and it consists of eigenvectors of the matrix A that are also orthogonal to each other. Now, going back up here to this matrix P, we had a matrix that was consisted of eigenvectors, but it was not orthogonal because, for example, the two columns here, if you take their dot product, it's 1 and not 0. And that can happen because this matrix here has a repeated eigenvalue. So, okay, anyway, so the Gram-Schmidt process to these three vectors that are the columns, what it does is, okay, the first vector, it just takes as the vectors of our new basis. For the second vector, for the next vector, what we do is we take the given second vector and then subtract off the projection of the first vector onto the second vector. So here we see that our answer of this matrix R has the same first column, but I think the second column, well, that turns out to be the same, it looks like, but anyway. Okay, and so then the third column is certainly changed. Okay, so this is what the Gram-Schmidt process gives us, but as we see this first column, its norm is 3 or square root of 3, and so we need to just normalize down to 1. And so I just wrote a very short routine or function or whatever that takes a matrix. I'm calling it normalize columns. And what does it return? Well, okay, this first command, column matrix, is just saying we're going to give it a list. And let's let me start on the right here. Basically, m.columns just gives the list of the columns of this matrix M. And then for each column of M, what I do is I call that column V. I take V divided by the norm of V. So this first column here, I'm going to take the 1, 1, 1, divide by the norm of 1, 1, 1, which is root 3. And then doing the same thing for all the columns, and then throwing that together in a matrix, I get this function here that's returns. So, okay, let's try this to this function, apply this function to this matrix R. And there we have it. You can see that this 1, 1, 1 has turned into this column here. They've rationalized the denominator. So that's why it's written like this, but this is the same as 1 divided by root 3, 1 divided by root 3, and finally 1 divided by root 3. It's a little bit easier to see, well, maybe not. Okay, anyway, so that's this, and so that's what the answer, what P should be, our matrix of eigenvectors that is orthogonal, orthogonal. So let's check that it's orthogonal. To do that, we need to check that P transpose P is the identity matrix. We should probably also check that P times P transpose is the identity matrix as well. Times P dot transpose. That's also the identity matrix. So P is an orthogonal matrix. And then let's check this other final property that P times our diagonal matrix times P inverse is our original matrix A, which is correct. All right, so let's go back to Anton and look at the answer here. Whoops. Answer. Not sure why it's not showing me the answer. Oh, there it is. Okay, so the answer, looks a little bit different, and that's because if you look at the diagonal matrix here, they have it 3, 3, and 0 as listed, and our diagonal matrix here that Sage Math gave, let's ask for D, is 0, 3, 3. So they've listed the eigen values in a different order, and you also might find a different a different basis for each eigenspace, and so basically there's more than one possible answer. But how do I know this answer is correct? Well, I just now checked that I get P times D times P inverse is the original matrix A, or equivalently P inverse times A times P is a diagonal matrix.